Hey, before the video begins, I realized something that would have been really helpful before I started the video, and that's just reviewing like how do you draw slopes. And I want to refresh your memory on this very quickly before the video begins. This, guys, what is the slope of this? This this tangent line, a horizontal line. What is the slope of that? The slope of that is 0. The slope is 0, right? So, your derivative is 0. You can think of it like that. Or your m is 0, or your slope is 0, whatever, it's all the same thing. Okay, what about this? What's the slope with that? Well, I don't know exactly. Maybe it's 1, right? It could be 1. Okay, and then how about this one? Well, that could be 2, right? Okay, how about this one? Like -1, right? Okay, I just want to go over that because that's what you're doing today. And if you don't understand like what's going on here, you're gonna have a hard time. That's it. Enjoy the video. Okay, we're gonna get started here. Um, this is the lesson 6.5 notes for and walkthrough for slope fields. So we're on the last lesson of Unit 6, and I'm sorry I couldn't be there today. It's a bummer because it's kind of a fun lesson. If I was there in person, it's kind of a cool activity, but I promise to make that up to you in Unit 7. We got Play-Doh. I don't want to hype things up too much because it's Play-Doh and there's limes in Unit 7, so get excited. And I just want to say before we begin, I just want to say you guys are doing great. You're all doing really, really well. You're working hard, and I'm extremely, extremely happy and proud of you all. So keep it up. You're doing so well. We're in the home straight. All right, let's get started. How do I draw a slope field? Let's look at this differential equation dy dx equals x. Recall that it represents the slopes of the tangent lines of a function. Let's look at it on the graph. At right are the tangent lines for x equals 2. Why do all the tangent lines have the same slope at x equals 2? Well, remember, uh, this is slope, right? So I just want to remember, like in your head, think of derivative as slope, right? I've been saying that since the beginning of the year. It's like a really easy way to think about the derivative. It's the slope at a point, right? So this is telling me at 2, my slope is uh, 2, right? When I plug in 2 into this, I get 2, right? Because the derivative at x equals 2 is 2, right? So what about the slopes for the other values? Well, it's pretty straightforward because it's just the same because the derivative is just x. So the slope here is -4. Slope here is -3. Slope here is -2. Slope here is -1. Slope here is 0. Slope here is 1, 2, 3, 4, and so on. So what does that look like here? So what we're doing here is you are sketching a little mini slope. So these little ticks here, they're slopes. This is specifically a slope of 2, right? A derivative of 2, a slope of 2. So when x equals 1, my slope is 1. So the way that you draw that is you do a tick, but it's not going to be quite as steep, right? Uh, you're gonna, the way that I'm drawing it right now is that I'm angling it as if it was going to hit that corner right here, because that would be a slope of 1. Doesn't have to be perfect, guys. Doesn't have to be anything special, especially when we get to these ones right here, because these ones are going to be even steeper. And so it doesn't have to be perfect, nothing insane. But you just want to show it's generally getting steeper. And here it's getting really steep. Okay, got it? See that? So we're getting steeper. And at 0, my slope is 0. So it's just horizontal lines going through here. Okay, and then at -1, we're going down 1, down 1, down 1, bit steeper, right? Again, it doesn't have to be perfect, but it should be steeper, a little bit steeper, and a little bit steeper. Okay, so this is showing the slope. This is showing a differential equation. So we did that. We filled in the slopes. Let's keep going. Each of the lines shown are small tangent lines. Yeah, small slopes, right? Through every point from -3 to 3 of the differential function we are working with, dy dx equals x. This type of graph is referred to as a slope field. Very important. Okay, slope field. The slope field reveals that the antiderivative of dy dx equals x is y equals 1/2 x squared plus c. Use differentiation to support this. Okay. Well, this is just saying take the derivative. So when we take the derivative of this, yes, we do get x. So I guess my question is, how does this reveal that the antiderivative is this? Well, if you look at the slope field, you notice like you see kind of a pattern here. What do you see? What shape do you kind of see within this? What's this shape here? It's a parabola, right? This is a parabola right here. Okay? And we see many parabolas, like they're kind of on top of each other like this, many parabolas. Well, that's showing the C right here. Because the C has infinite solutions. So you're kind of graphing infinite solutions on this on the slope field. All the solutions are here. Okay, depending, I can pick any C I want, and I can get a solution there, right? And that's what we're going to do in C. There are many solutions to a differential equation. What do we mean by solution? How many are there? Well, solution is a particular equation, right? And that's what you've been doing, a particular equation. That's what you've been doing in the delta, last delta, you were solving for it. And there's infinitely many of them, because C can be anything. Infinite solutions, okay? So if we want the particular solution of -3, 1, if we go up here, you go to -3, 1, 2, 3, 1. I'm going to sketch, this is very important. So, like, very important, look at what I'm doing right now. This is an easy point on the test. Okay, I'm looking for the particular solution at -3, 1. I go to -3, 1, 2, 3, up 1, and I just sketch like it's water. Like you want to enter this. It's like, imagine this is like a current, and you're like a leaf that's dropped in the current, and you're just being swept away by these ticks, right? Elman knows what I'm talking about, like water, right? So when you go here, I'm just gonna, I'll do this in a different color, do some purple. I'm gonna start at -3, 1 because that's what I'm given, and I'm gonna be like water. I'm just gonna be a leaf that's being taken by the current, and I'm just following. It's like connect the dots almost. I'm following the curve. So this purple curve that I drew, this is the particular solution. And all of these, everything here, these are all these other ticks, all these other places that we could draw curves, those would all be the general solutions. And if I pick a point and I draw my curve through it, that's particular, but everything else, those are all general solutions. Okay. Let's keep going here. Let's sketch some slope fields. So at this point, guys, if you understand what's going on, trying these by yourselves. If you don't really get what's going on, follow with me. Okay. dy dx is -2y. Sketch the slope field to the right. Compare and contrast. Okay, so all this means is you're going to get the slope by multiplying the y value by -2. So, for example, right here, my y here is 0, right, at this point. So that means all my slopes are going to be 0. because the y value is 0. Always are 0 because the y value is 0. What's my y value here? 1, correct? That means all my slopes are going to be what? They're all going to be -2. So I'll draw like, and this is not going to be accurate. I have to kind of draw it inaccurately so that I can, because it's going to get steeper as I go up. What's my y value here? 2. So my slope is 2 times -2, right? If y equals 2, then my slope is -2 times 2. So my slope is -4. So it's going to be even steeper, like this. Okay? How about down here? My value is -1. Y value is -1. Plug that in. -2 times -1 is 2. So it's going to be this positive slope, like this. Right? And then we're going to go down to -2, so my slope is going to be +4. So it's going to be like steeper, like this. Okay? Got it? That's a slope field. That's how it works. You plug in the coordinates, you plug in the y or the x values into the derivative, and that lets you sketch that tangent line. It's a slope, right? If I'm not making sense here, think about it. Okay, look at my pen, right? This is slope. What's the slope of this? The slope of this is 0. What's the slope of this? Something positive, maybe 1, maybe 2, right? This is more steep. This is like 3, 4, 5, getting steeper. Back down to 0. Go back down. Now it's negative. -2, -4, -7, right? Whatever. Back to 0. That's what you're doing. You are finding, where's the pen going? Is it going up? Is it going down? Is it going flat? You're plugging in these points to find that out. So what do you notice about this, right? You can see parallel, all these slopes are parallel by rows. If we go back to the other one, they're all parallel by columns. All the columns are the same. Okay, that's very important. Okay, x plus y. This is a little bit more tricky because you have to include both the coordinates. So let's pick one together. So for example, 1, 1, right? X equals 1, y equals 1. That means my slope will be 1 plus 1, which is 2. So my slope here at 1 would be 2. So I got it roughly like this, right? Okay. Now let's go one backwards. So now my slope, my x value here is what? My x value is now my x value is 0, right? So my slope is now going to be at x equals 0 and y equals 1. My slope is 0 plus 1, which is 1. So the slope here is a little more shallow, something like this. And here I'm at -1. X is -1, y is 1, right? X equals -1, y is 1. And that would be -1 plus 1 is 0. So right here my slope is 0. You see what's going on here? Okay. Well, if I kept going, well then I'm going to have -2 plus 1. So it's now going to be negative here. Something kind of slightly negative. It's going to be slightly more negative. And you notice there's patterns here. So all of these, you want to like identify those patterns. All of these are going to be 0 slope because their x and y's are opposite. See 4, -4, 3, -3, and so on. So all of these are going to be horizontal. And all of these, you're going to have this parallel style by diagonals. Because here, here and here, these 2 points here are the same. Because the y value is 1 more than the x value. So all these are going to have a slope of 1. And all these are going to have a slope of 2, right? That. And these are all zeros. These are all going to be like -1s. And these are all going to be -2s, right? So this one is, so this one's parallel by rows. This one's parallel by diagonal. Okay. How about this one? Y over x. All right. So if you're like, I don't know how to do this, just pick points. Pick easy points. Pick whatever you want, right? So for one thing you can do to make it easy is pick numbers that are very nice, that work really well. So for example, y equals 0. If I put 0 in the top of here, it doesn't matter what x is. 0 is always going to be 0. So all these here, 0, 0, 0. They're all slope of 0. Remember, horizontal means 0. That's 0. Okay? How about if x is 1? If x equals 1, then the slope is whatever y is, right? Because it's just divided by 1. So whatever y is the slope. So here at 1, I'm going to have a slope of 1, then 2, then 3, then 4, and -1, -2, and -3, and -4, like that. What about if x is 2? Well, if x is 2, then it is whatever y is, but in half. So whatever y was in half. So instead of 1 right here, this is actually 1/2. Even shallower. This is just 1 now. This will be 3/2, so like in shallower. And that's 2, right? And same here, like really, really shallow, 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 right? Okay. See how that's working? So you're picking points, you're plugging them in, and you're looking for patterns that are going to happen. You're looking for easy points that you can do. So when 0 is easy because those are all 0. When x is 1, so you go to the 1, x equals 1 column. Well, it's just, that means the slope is whatever y is, because y is on top. So this, we'll do the same thing. X equals -1 is going to be good, because it's going to be whatever y is, but negative. So it's just going to be the opposite of this one, right? So where that one's up, it's going to be down, more down, more down, and so on. I'm not perfect at this, guys. And this one's the same thing, but shallower, because it's gonna, when x is -2, it's whatever y is divided by -2, so it's gonna be whatever y is, but negative, but a half of it, right? So it's gonna be negative, very, very shallow here, shallower. Okay, same thing here, pretty shallow, getting a little steeper. Okay, it's not perfect, but this is roughly how it should look. And I think drawing the ticks is not easy. And I will, you know what, I've noticed that just by drawing this, it would be very helpful to put in a little lesson about this at the beginning. So I'll talk about slope in an extra little video I'll put at the beginning of this. Let's keep going. We're nearly done. So Diana drew the slope fields below, but forgot to label them with their differential equations. Her teammates, Lucy and Sydney, decide to help her out, but they are not sure how to proceed. They know that the differential equations are, okay, sorry, I did not have that centered. Dy dx is 3 minus y, dy dx is x plus y, dy dx equals x, dy dx equals negative sine x. Okay, so this is very common. This is like an AP style question, where AP style questions like gives you the slope field, it says which one of these matches it, or it'll give you one of these and it'll tell you which one of these matches it. Like this, like that's the AP questions that you get here, generally speaking. Okay, let's look at A. A says Lucy suggests using implicit integration to solve each differential equation and find a match. Explain Lucy's method. What does this mean? Well, what it means is you can't always do this. If we think about dy dx, right, equals x, I'm doing this one right here because this is an easy one to do it for. Think about that. And if I solve this, and this is a very easy one to solve because I don't have to separate it or anything, I can just integrate it as it is, right? Because it's just x. This is just y equals 1/2 x squared plus c. So what that means is you can look at this and you're looking for a squared function, a parabola. So you say, okay, which one of these has a parabola? Well, D has a parabola. This must be dy dx equals x because the solution is this parabola. Look at this. See it in there? It's a parabola. It's 1/2 x squared plus a c. That is that. Okay? B. Sydney says all you have to do is pick a few coordinate points and substitute them into the differential equation. This is my preferred method, and this is what I would do in the AP test. This is what I like. So let's say you wanted to test for 3 minus y. Let's say like, okay, I'm going to start testing this one. All you have to do is pick some y values here and plug them into this and see if it works. So for example, that's what we're doing. Plug in values, see if it works. I mean, I don't know how to explain that. It's what she says, right? So we go up here and okay, let's test this one. So okay, I'm gonna just test like y is 3. So if I plug a 3 into this, I should get what? I should get 0. But here I don't get 0 at 3. See that? I don't get 0 at 3. If I plugged in a 4, I should be getting 1, 1, 1, 1, 1. I should be getting a slope that looks like this the whole time. But I don't. I get this weird like up-down pattern. So that cannot be A. If you look at B, I can do the same test. When I plug in a 3, I should be getting zeros. I don't get zeros. At 4, I should be getting just straight 1s. And it's changing, so that's not true either. Then let's check C. At 3, it's not showing me at 3 because it's kind of like they didn't mark it at 3, it looks like. But if you look at 4, for example, or just above 4, I am getting that -1 each time, right? 3 minus 4 would be -1. It must be C. Okay, this must be dy dx equals 3 minus y because when I plug in 4, I consistently get -1. Okay, you don't have to show your work. You just do it, right? Now, what does Diana say? Diana thinks that her friend's method will take too much time. All you have to do is look at the orientation of the parallel and tangent lines. Explain Diana's method. Okay, what this one is talking about is that, and this is going back to the previous examples, when a differential equation is only written in terms of y, that means all of the rows are going to be parallel, right? That's this. If the differential equation is only written in terms of x, like the first one, then all the columns are parallel. Okay, so that's a way that you can eliminate them. So if you notice for this one right here, see how all the rows are parallel? That indicates that it can only have y in it. See how all the columns are parallel here? That means that it has the x, or only an x variable. The same goes for this negative sign. See how it has x in it? That means that all the columns should be parallel. So that means that, see how all these are parallel here? Yeah. And you can also see, based on this wave, it's a trig function, right? This is dy dx equals negative sine x, okay? Which means that this must be x plus y. Okay? All right. Good. Well, that's the classwork pretty much. I hope that makes sense. Let's do the toolkit. I'm on the toolkit. Last page of the toolkit, 6.4 slope fields. This is the toolkit, last page. Slope fields are graphical representations of a differential equation and lets us visualize the family of the particular solution curve. So again, the family means this means like general solution. It's just like talking about you're seeing all of them. You're not seeing one solution. You're seeing all of them. So how do you make it? I mean, plug in the points. Plug in coordinates into differential equation, and then estimate slope with ticks. Okay, tangent lines. Okay, A solution curve will follow the trend of the slopes and must pass through the initial condition if given. If dy dx is undefined, there's no slope at the point on the slope field. Okay, what that's saying is if you had like uh, y over x and and x was 0, that means no slope. Like it's just blank there. Okay. Slope fields are useful for helping us find solutions to differential equations that cannot be integrated when analytics fails or become too time consuming. The graph of the solution can be approximated with a slope field. Okay. So example, the slope of the differential equation dy dx is negative y over x is shown at right. Using an implicit integration, the solution of this differential equation can be shown to be y equals c over x, a hyperbola. The particular solution going through 3, 3 is shown. Notice that only one arm of the hyperbola is revealed on the slope field. Okay. So that's it. Remember, this is the particular solution. So do the delta, and once you do that, do the practice test. I'll post a video this weekend. Have a great weekend. I'll see you on Monday. Well, I'll see you on Friday with block 4.